SPC chart example C. Very similar to examples A and B, but just a few minor differences I think I need to spend some time talking about. Today we're going to be measuring micro SD card thicknesses. I don't know if this is the right dimensions or not. I just made some guesses at it. And notice that I said round to the third decimal place in all calculations, and there's an example of the 3 decimal place calculation, how to round. And let's see, let's go ahead, and our sample size is n equals 6. So let's jump on over and take a look at some of the answers I've worked out for you. And before we do that, like I've said in the past videos, I recommend that you try to solve these yourself or with your group prior to looking at the example answers, because again, you might assume that you know something by looking at the answers, but when you try to do it by hand, maybe some confusion occurs. And here we go, and I went through and I marked the ones that did not meet engineering specifications for later on, the 3 ones in red. This is 0.212, which exceeds that. This is 0.095, which is less than that, and this is 0.205, which is greater than that. So those are the points that exceed the specifications for later on, a question near the end. As before, ignore this number. It's just a random number generator that I use. Okay, X bar, third time. We'll say it one more time. It's the average of these 6 numbers goes there. The average of these 6 numbers go here, all the way down for your X bar, which is just another name for average. And to find the average, it's adding up the 6 numbers and divided by 6. Add up the 6 numbers, divide by 6. For range is the largest number here, which would be 0.176. Subtract it from the smallest number. Alright, you calculate the biggest number minus the smallest number there, the biggest number minus the smallest number to come up with this, all the way down to get your ranges. Like before, you take the average of your averages to get your X bar, so the average of these. The average of the R's is the R bar, and that number goes there. These numbers will be used in our calculations of control limits, not specification, but control limits. Also notice that sample size n equals 6, 1, 2, 3, 4, 5, 6. We are going to be using these numbers, 0.483 for A2, 0 for D3, and 2.004 for D4. So X bar, that's just that number. R bar is that number, so we have those two covered. But when we look at lower control limit for X bar, it's going to be X bar, 0.150 minus 0.483 times R bar to come up with this number. To come up with the upper control limit for X bar, you're going to take this number plus this number times this number. So for the lower control limit, it's a subtraction, the average minus A2 times R bar. For the upper control limit, it's X double bar plus A2 times R bar. So for the lower control limit for the ranges, or R, it's just 0 times the R bar, which is 0. The upper control limit for R is simply 2.004 times 0.084, and you'll come up with that number, hopefully. Here's our engineering specifications, like I mentioned earlier. Again, we ignore this, and so we've got this calculated. We already calculated this, and remember the green stuff, that's just for my use when I'm creating these graphs. And here is my X bar chart. Again, where's my process average doing? How's it changing? And if I look at this one, the X bar chart is in control. The average chart is in control. Now, no point exceeds the lower control limit. No point exceeds the upper control limit. So this X bar chart or average chart is in control. The R chart lower control limit, the average R, upper control limit for R, and everything falls where it should. And so that's why it's a little bit different scenario than example A and B. And then I would say for my comments, my X bar chart is in control. It's predictable because none of the averages exceed the upper control limit or lower control limit. It really should be lower. Specifically, we are 99% sure that our process average has not shifted due to an assignable cause, a specific cause, not just random variation. No investigation into a root cause is presently needed. You'll need to make those comments. It's in control, the 99.73%. If it was out of control, you tell me where it occurred, and you're going to tell me whether or not an investigation into the root cause is needed. The R chart, we're looking at this one. R chart is in control because none of the range values exceed the lower control limit or upper control limit. Specifically, we are 99.73% sure that nothing has caused our process variation to increase. This one has to do with our process average, the X bar. The R has to do with variation. Don't mess that up on the exam. And we need not investigate since the R chart is in control. Are we currently producing stuff that does not meet engineering specifications? Yes. Even though the X bar and R charts are in control, some of the SD cards exceed the engineering specifications, or the USL and LSL. At 1 a.m., the second SD card was found to be above the USL, and there it was. And so let's take a look at 1 a.m. I'm saying at 1 a.m. the second reading measurement was found to be 0.212. I will go on to say at 3 a.m. there was a problem with it being too low at the second measurement. And of course I will also say at 6 a.m. the fifth measurement will exceed it. And if we look at this, it says at 1 a.m. the second SD card was found to be above the upper specification limit. That's the value it was. At 3 a.m. the second SD card measured was found to be below the lower specification limit. There it was. At 6 a.m. the fifth SD card was found to be above. And very, very similar to what we've done in the past.